The effect of lone pairs. So right before this, we looked at valence bond theory and just the electron groups around without specifying lone pairs from bonds and what that might do repulsion-wise. So what happens in a molecule that has lone pairs around the central atom? Lone pair electrons also repel one another along with the electrons in bonds. Lone pair electrons typically actually exert a greater repulsion than bonding electrons. Why could that be the case? So let's do two examples. Let's draw two examples. We have water with the lone pair. And then we have carbon dioxide with the double bond. The reason I drew both of these is because they both just have two groups of bonds around it, but one has a lone pair, right? So this has two bonding groups around the central. Here we have two bonding groups, two lone pairs. What happens is the lone pairs push these bonds down to create a bent shape here. Now, the lone pairs, they repel each other, right? However, they have a greater force because they are not also being attracted to the nucleus of another atom. Now, the electrons in a bond are being repelled by one another, and they're being attracted to the nucleus of one atom and the nucleus of the other. In a lone pair, there's repulsion going on, and there's attraction going on. But the attraction is only towards the nucleus of the oxygen, whereas the electrons in the bonds have attraction with the nucleus of the hydrogen and the nucleus of the oxygen. Therefore, since there's less attraction for lone pairs, these have a greater force of repulsion, which therefore causes bonds to bend more, changing the geometry. The lone pair is stronger, lone pair bonding, and then bonding pairs. The effects of the bond angles making them smaller than expected. The effect of lone pairs. So this is basically a summary of what I just said. A lone electron pair is more spread out in space than a bonding electron pair because a lone pair is more attracted to not only one nucleus, but also two. So here's an example. Here we have a bonding pair, right? You have the nucleus in the middle, you have the electrons being attracted towards both nucleuses. Here, for a non-bonding pair, you only feel one attraction of a nucleus rather than both, so this has greater repulsion. Now let's look at the different shapes that we can have. So when we have three electron groups, we already talked about, we're looking at central atom, 1, 2, 3, 3 electron groups. I know that that's trigonal planar. We already talked about that. So the trigonal planar, when I'm just looking at my electrons, is my electron geometry. So when you're asked for just the electron geometry of a molecule, you're just looking at the electron groups. You're not specifying what are bonds and what are lone pairs. If you're asked for the molecular shape or molecular geometry, then you have to say, okay, out of these three, what are my bonds? What are my lone pairs? What is my three-dimensional shape actually looking like due to the correct repulsions? So for this structure, I have one lone pair, and then I have this group of bonds and this group of bonds, so two bonding groups. Now again, a way to check is that your lone pairs, so your non-bonding electron groups, it can be named the same thing, and bonding have to add up to your total electron. If you've gotten different numbers, then there's something wrong, and you can always double check. When you have a lone pair, two bonding groups, you have a bent shape. So basically, this is three electron groups around the element, the central atom, but then the repulsions from the lone pair pushes those two bonds further down, causing a bent shape, and therefore, instead of being 120 degrees, it's now less than, the bond angle is less than 120 because the electrons are pushed down a little bit more. When we have four electron groups, we already talked about how that's tetrahedral, and that's 190 degrees. Now, if you have 1, 2, 3, 4 electron groups, electron geometry is tetrahedral. Now here I have three bonding groups, and one lone pair. Again, you have to make sure they add up together, and they do. And then you can see that this lone pair has extra repulsion and will push those bonds further away from it, giving a 107 degree, so less than 109.5, which isn't good enough to say. You don't have to remember the 107. This is the ideal tetrahedral geometry where we have 109.5, but due to the repulsion of the lone pair, you form a less than 109.5 degrees. Now, what if you still have 4 groups, but you have more lone pairs? So for water, for example, if I redraw my water from before, I have 1, 2, 3, 4 electron groups. I have 2 bonding groups, and I have 2 lone pairs. Now again, everything has to add up to the total electron groups. Now, because I have these 2 lone pairs, not only do they repel the bonding electrons, they repel the other lone pair even more. This causes those angles to further push away from one another and creates that bent shape, which is then an even lesser 109.5 degree angle. Even smaller. Lesser is not a real word, I don't think. Anyways, an even smaller 109.5 degrees of an angle. Alrighty, so the actual angle for a bent tetrahedral shape is 104.5. Again, I will be totally satisfied with you knowing that that's less than 109.5, since the electron repulsion when there's one lone pair is a little bit less than 109.5, and then when there's an extra lone pair, it bends even more. Now, a different example. We see this example of chloride, Cl2 minus, ClO2 minus. I have 1, 2, 3, 4 electron groups, 2 bonding groups, 2 lone pairs. Therefore, I create a bent molecular shape, or a geometry, and a tetrahedral electron geometry. And my bond angle is less than 109.5 degrees. So that's just a summary of what we already learned. Now, the effect of lone pairs. So when we have 5, it gets a little bit different. We learned that for 5 electron groups, we have a trigonal bipyramidal, and we have a 90 degree and 120 degree, axial, equatorial. Okay, however, when it's not just 5 bonds, it changes. So if you have a 5 electron groups, 1, 2, 3, 4, 5, but one of them is a lone pair, then your molecular geometry is a little bit different. Your molecular geometry then becomes, I'm going to show you the chart, for 5 electron groups around the atom and 1 lone pair. The electron geometry is trigonal bipyramidal, and the molecular geometry will be pushing the bonds a little bit further away from itself because of that lone pair. And when you have 4 bonds and 1 lone pair, you have a seesaw. So I'm going to write bonding pairs, 1 lone pair for 5 electron groups, seesaw, with less than 120 for equatorial, less than 90, giving you this kind of a shape because of the repulsions. Now, what if we have 5 groups but 2 lone pairs? 1, 2, 3, 4, 5, 2 lone pairs. 5 electron groups, 3 bonding pairs, 2 lone pairs. I now have T-shaped. And my bond angle is just less than 90. Because you can see here that since these are in clouds of the electrons, the shape's coming from here. Last one for the 5 electron groups is when you have a linear shape all of a sudden. So if you have 1, 2, 3, 4, 5 electron groups, 2 bonding pair groups, and then you have 3 lone pairs, the repulsion of the lone pairs causes both bonds to then form a linear structure, where we already know that the bond angle for linear would then just be 180 degrees. Then the basic arrangement for the last one was octahedral. So for octahedral, it's very similar to trigonal bipyramidal. Before I get there, looking at the summaries of the main ones that you'll see. There's 2 electron groups, 3 and 4, bonding, lone pair, electron geometry, molecular, the bond angles, and some examples. For when you have 6 electron groups, we learned that that's octahedral. Now, if I have 6 electron groups, 5 of them are bonding pairs, and 1 is a lone pair, I have a square pyramidal. For example, bromine with 5 fluorines around it. One, 2, 3, 4, 5, 6, 5 bonds, 1 lone pair. That gives me a square pyramidal shape with less than 90 degrees. Another one, and the last one possible, is 6 electron groups, 4 bonding pairs, and 2 lone pairs. This gives me a square planar geometry. For example, when you have xenon that has 4 fluorines. 1, 2, 3, 4, 5, 6, 4 bonds, 2 lone pairs. You create a square planar which looks just like it's in the plane of the paper and gives you exactly a 90-degree angle. And those are all of your electron arrangements. So, when drawing Lewis structures and determining the shape, you can go step by step. So if we figure it out together for ammonia, first draw the Lewis structure for ammonia. N, H, 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 NH3. Then you want to determine the total number of electron groups. 1, 2, 3, 4. 4 electron groups. Then determine the number of bonding groups. 1, 2, 3. 3 bonding groups. And then you see if you have any lone pairs. I have 1 lone pair. And then you would figure out, well, based off of my table, what is that? Well, I have 4, so I'm in this column. 3 of them are my bonding groups, 1 are my lone pairs. So my electron geometry is tetrahedral. My molecular geometry, molecular shape, is trigonal pyramidal. And my bond angle is less than 109.5 degrees. Now let's put that into practice. Predict the shape and bond angles for the following. So here I have phosphorus and 3 chlorines. Since we've practiced Lewis structures a lot, I'm going a little bit fast through this part, but please feel free to pause and work through the Lewis structures on your own. Now, double checking, I have 5 valence electrons for phosphorus, I have 7 for chlorine, but I have 3 of them, so 21 plus 5 is 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and each satisfies the octet. Awesome. Now determining my shape. 1, 2, 3, 4 electron groups, 3 bonding pairs, 1 lone pair. I have since I'm just looking for shape, looking for the molecular, because it's always when it's just written shape, you're just looking for molecular geometry, trigonal pyramidal, and my bond angle is less than 109.5. Alright, next one. Here we have an ion. So I have 7 electrons for iodide. I have 4 times 7 for chlorine, and then I have an extra 1. So 28 plus 8 will give me 36 electrons. So iodide, chlorine, 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 and chlorine. I know that the chlorines have to bond. I know that the chlorines are in group 2, so I can't, in period 2, so I can't expand an octet. So each of my chlorines are satisfied. I now have 8 times 4, which is 32. So I have 4 more electrons. Well, since iodide is in period 3, it can expand my octet, and my extra electrons will go to the iodide. Now, how many total groups of electrons do I have? 1, 2, 3, 4, 5, 6. 6 electron groups. 1, 2, 3, 4 bonding pairs, 2 lone pairs. This shape is, from the chart, what we just talked about with the octahedral shape, when we have 6 electron groups for bonding 1 lone pair, square, planar. And my angle is 90 degrees. Last one, chlorine, 7 electrons, nitrogen 5, oxygen 6. This is 18. Nitrogen can bond the most, so it makes sense for nitrogen to be in the middle and the chlorine and the oxygen to be around. Now, if I assign all my valence, just to do a little bit of a different method, I know I've used all my electrons. Well, I know I can bond the chlorine and the nitrogen just the one time. And then I can bond the nitrogen and the oxygen twice. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. 4, 6, 8, 10, 12, 14, 16, 18. Perfect. Now, the nitrogen has, let me clean this up a little bit because it looks kind of messy. So the nitrogen has 1, 2, 3. 3 electron groups. 2 of those are bonding pairs, and then 1 lone pair. So the repulsion comes from the lone pair. This is a bent shape and has less than 120 degrees. So important when figuring out the shape, if it just says predict the shape, you're looking for molecular geometry. If it says electron geometry, you're looking for only the shape that's caused by the electron groups. Molecular shape comes from actually the repulsion of the lone pairs. Draw out your Lewis structure with the lone pairs and all the bonds and electrons. Go through how many groups total you have around, then separate between bonds and lone pairs. They always have to add up to your total amount of electron groups, and from there you figure out your shapes following along the chart.